Hello, and thank you for joining us. Today's presentation is comparing EPA method 8260C and D. Our presenter today is Jeremiah Bradley, Applications Chemist for Teledyne Tekmar. Feel free to submit your questions throughout the presentation, and we will respond individually after the webinar has concluded. This webinar is being recorded and will be available within a couple of days. Now I'll turn it over to our presenter, Jeremiah Bradley.
Hi everyone, and welcome to Texas University e-learning webinar series. Today's webinar topic will be comparing EPA method 8260C and D. Feel free to type your questions as we go along, and I'll try to address them as we can or towards the end if time permits. For those who are new here, I'd like to start with a brief background on Teledyne Tekmar and give you a quick overview on Persian trap. Tekmar is a leader in design and manufacture of analytical instruments for laboratories providing productivity enhancement, instrumentation, and solutions to several industries. Our world-renowned product line include VOC, volatile organic carbons, systems for gas chromatography sample introductions, including high-throughput purge and trap sample concentration and sample automation. Additionally, Tekmar manufactures a line of total organic carbon analyzers which provide unparalleled accuracy, precision, throughput, and reverse for water samples. This webinar will cover EPA method 8260 and compare the changes from C to D, while providing a brief introduction to the sample prep methods 5030 and 5035 using the Atomic XYZ. We will also cover a few of the challenges, observations, and tips for the method that were important to keep in mind, as well as some of the results. So what is Persian trap? First, a measured amount of sample is placed in a 40 milliliter VOA valve. Then the sample is purged with an inert gas, which strips the VOCs out of the sample and deposits them onto an analytical trap. Upon desorb, the trap is heated and the VOCs are swept onto the trap GC column by backflushing the trap with an inert gas. The purge gas used in this demonstration was nitrogen. Here's a brief review of the autosampler used for today's topic. Tekmar's Atomic XYZ is a purge and trap concentrator with a built-in multi-matrix autosampler. It can run water, low-level soil, and methanol extraction samples. It has 84 positions for 40 milliliter VOA valves and offers an optional chiller tray for cold preservation of the samples. The Atomic XYZ also features a patented dual-stage water heater and methanol rinsing capabilities, which reduces carryovers. This is very helpful, especially when working with highly concentrated samples that require methanol extractions. It is the first of its kind with automatic methanol extraction, which is very helpful for US EPA 5035 users, as it will save you time and effort when preparing extraction samples. The mass flow controller is optimized for helium and nitrogen, meaning that either gas can be used reliably and accurately for Persian trap analysis. Additionally, the mass flow controller makes it easier to keep track of pressure and locate any leaks for proper maintenance. Lastly, the Atomic XYZ has a moisture control system to help reduce the amount of water that reaches your trap, extending the life of the GC column. The Atomic XYZ method 5030 capabilities include automatically withdrawing up to 25 milliliters of the aqueous sample volume into the sparger. The Atomic XYZ capabilities of the EPA 5035. In the EPA method 5035, there are two methods for extractions. For the low level of 5 to 200 ppb, the methanol extraction is unnecessary, and the sample is purged directly into a 40 milliliter valve. Using a patented three-stage needle, the volatile compounds are swept directly onto the trap. This technique is known as the soil mode for the Atomic XYZ. For the soil samples with concentrations higher than 200 ppb, methanol extraction is required. For this, the Atomic XYZ automatically adds methanol to the valve, stirs it using a magnetic stir bar that is placed in the valve by the analyst, and then transfers the aliquot of the methanolic extract to a 5 milliliter sample volume of DI water. This technique is referred to as a methanol extraction mode. EPA method 5030 utilizes the water mode of the Atomic XYZ. Note that clean water blanks drawn from the reservoir are not the same as the method blanks and should not be used as such. EPA method 5035 utilizes the solid mode of the atomic XYZ for low-level in-valve purge. Keep in mind whatever is in the empty headspace of the valve will also be purged into your blank and appear in your TIC. Therefore, any laboratory air contamination may cause elevated background and therefore elevate your MRLs. The latest 8260 method is revision D. While D incorporates the expansion and guidance of using hydrogen as a carrier gas, EPA method 8260 is a determinative method used to analyze volatile organic compounds in a variety of solid waste and water matrices. Some formal changes from its previous C includes terminologies like area or height has been changed to response, and mass has been changed to MZ. Furthermore, tune updates have gone from once every 12 hours to once prior to initial calibration. I think it's also important to note that within the BFB tune, the relative abundance of ion 96 has been expanded from 5 to 15% when using hydrogen. With respect to terminology in QC, we have several factors that remained unchanged from 8260C. These control types, frequencies, and recommended acceptance criteria remain the same. I created a convenient table in the upcoming slide to demonstrate the expectations and guidelines. A few changes worth noting when changes that are made from C to D is the instrument performance check. Now, prior to initial calibration, is no longer done every 12 hours as mentioned before, and this model was modeled after the 524.3 tune criteria. The initial calibration was also updated and reorganized, which I'll talk a little bit farther about in the next upcoming slide. The blanks were given a little bit more specific details in terms of passing criteria. So now it must be ran after initial calibration and prior to sample. The method blanks must also be less than 1/2 of the LLOQ or 1/10 of the sample concentration. The internal standards were also specified with the initial calibration, or CCV, will be compared to the midpoint of the initial calibration. And the annual verifications of LLOQ are performed annually or after any significant changes that are made. As mentioned previously, here is the QC requirements regarding the system calibration. So there's 3 calibration models: the response factor, the linear, and quadratic regression model. All 3 models require 2 standard sources. The first source is used to create an initial calibration curve, while the second source confirms the accuracy of the calibration. Additionally, the lowest standard must be less than or equal to the lower limit of quantification. Lastly, when each calibration point is quantified using the final calibration point, at or below the LLOQ must be quanted within 50% of the true value, while all other points must quant within 30% of the true value. The average response factor calibration model requires 20% or better RSD values for 90% or more of the analytes of interest. Both linear and quadratic regression models require an R-square value of at least 0.99 for the linear and 0.995 for the quadratic. The method blank, as I mentioned before, it has to be less than 1/2 of the LLOQ or 1/10 of the sample concentration. The calibration check verification is done again once every 12 hours, and at least 80% of those analytes have to have less than 20% difference with a 30% or a 30-second retention drift in terms of the internal standards. The IDP, or the initial demonstration of proficiency, needs at least 4 replicates to evaluate accuracy. Please refer to session 9.3 of method 8000 for more details. The internal standards response of the primary ions needs to be between 50 to 200% of the response in terms of the initial calibration midpoint. And the lower limit of quantification has to have the least calibration curve point, or it has to be less than or greater than or equal to the lowest calibration point, with verifications at 0.5 to 2 times the lower limit of quantification. Targets are recovered at plus or minus 20%. The laboratory control sample is done at 1 per batch of every 20 samples and must also meet the CCV criteria, while the matrix spikes are still done at a 1-to-1 ratio, with it being 1 matrix spike and 1 matrix spike duplicate per 20 samples. Please refer to section 9.5 of the method 8000 for more details. And surrogate recoveries are done at plus or minus 30%. 8260D also includes a guidance for using the hydrogen as a carrier gas. So I also wanted to take a little time to talk about the GC mass spec behavior when using hydrogen as a carrier gas. Hydrogen viscosity has a more broadly stable across a wide range of flow rate viscosities, allowing for a greater separation efficiency under the wider range conditions than helium. However, because of its highly reactive nature, hydrogen can alter the injection, column phase, and detector operation. For the injector reactive surface, preventative maintenance can be performed to reduce transformation. As for the chromatography, it's worth noting that the flow rate can impact the peak shape. The method author recommends using a narrow bore column from 0.8 or 0.18 millimeters ID or smaller, and a reduction in flow to reduce the pressure in the source to prevent chemical ionization in a hydrogen environment. We noticed that with the beneficial side effects of lower flow rates, it has improved the peak shapes. Lastly, you may notice the elevated background due to the hydrogen's reactivity. Just like any carrier gas, you may also likely notice a larger response factor value at the lower end of the curve and bias calculated ranges when using linear regression, or higher RSD values the lower you go. Specific to hydrogen, you may also notice a shorter retention time or retention time shifts, especially for gas compounds, peak splitting, and/or co-eluting. Lastly, you can expect to see dehydrogenation and sensitivity reduction for the reactive compounds. As a result, your tick may result in a higher or elevated baseline than when compared to helium. Here's a quick look at some of the concerns with hydrogen compared to its counterpart helium. Despite the very real concerns with reactivity, the flammability in hydrogen is drawing more attention as an alternative carrier gas, and it is less expensive and more readily available. Thanks to the revised tune parameters, passing the BFE tunes are attainable when using hydrogen as a carrier gas. Compared to helium, it is still able to pass BFE tunes while combating the helium shortcomings of supply and expense. First and foremost, safety is first. So be sure to check for leaks. Hydrogen is not only flammable, but is more prone to leaks and should be used with caution. Re-verify that your GC gas types to ensure that for proper flow throughout the system. Be sure to try slower flow rates and lower split ratio, as they may help to reduce protonation and increase sensitivity. You may notice that the source will require more frequent cleanings to prevent baseline evaluations. The liner may also be needed to be changed more frequently as well. Taken from the method, ketones, alcohol, ethers, and other water-soluble compounds will have lower responses. Elevated temperatures may be necessary during purging to exhibit better performances. You will also notice a low response for halogen due to dehalogenation caused by hydrogen. Water and methanol can cause interference that tends to co-elute with chloromethane and chloroethane, while aldehydes are known to have poor stability. Acetates are known to also have difficulties with reproducibility, response, recovery, and stability. Here's a brief list of compounds that are known to have difficulties with recovery via Persian trap, and please refer to section 1.3 of the method D for a complete list of trouble compounds. But if you're having any issue with these, you can try a direct inject approach. To demonstrate which ones are more successful, you'll see a list guided by Y, and the ones that you may still have a little bit of complications noted by N. Before we take a look at the results, here are some recent application guidelines that are used for parameters for GC MS that were currently used for this demonstration. Next, let's have a look at the Persian trap method parameters. Please note that these highlighted in yellow were not used in this demonstration, mainly being the pre-spurge times for both the water and soil were unnecessary, and the methanol rinses were also unnecessary. For the soil, we also were needed to use the heat for the sparge vessel, as well as the simple preheat time. Okay, and lastly, let's address the real-world example of the BFE tune in hydrogen. As previously mentioned, the major difference here being the 8260C and D is the expansion of the mass ion 96 relative abundance from 5 to 15%. You may have also noticed that the reference mass for the ion 95 is now 174. In addition, the target mass ion 50 and 75 are no longer used as a reference criteria within the updated version. With these new parameters, we are easily able to pass the BFE tune. For simplicity of 8260 compound list, here's a short list of the target compounds. All calibrations pass with a 0.99 linearity with less than or equal to 20% RSD. The ppb standards were used to calculate the MDL values for each target compound. So we still seen some denoted linear regressions that we had to use for compounds like acetone and hexachlorobutadiene, while we had to use a quadratic regression model for compounds like bromomethane. To generate a faster tick, here are the parameters used for the upcoming ticks comparing hydrogen and helium. Taking a closer look at the water method, here's a more recent tick we generated to highlight the difference and similarities between helium and hydrogen at 20 ppb. All the parameters and conditions were the same, only changes was the carrier gas. So the same trap, the same column, and the same simple parameters. With a quick comparison of hydrogen versus helium tick, you will likely notice hydrogen has a slightly shorter retention time and lower response, but will still able to provide sharp peaks. We see some separation with methylene chloride and acetone and coelution with diisopropyl ether and 1,1-dichloroethane. As I mentioned previously, because the hydrogen is a reactive gas, we see less response with some target compounds like chloroethane. Here's the middle of the tick. An interesting observation that we notice is the separation of the tetrachloroethylene and trans 1,3-dichloropropane when using hydrogen. As you can see, when using helium, we had some coelution. And similarly, benzene and methylacrylonitrile showed better separation than when used with helium. However, we saw coelution with pentafluorobenzene or benzene and 1,2-dichloroethane and hydrogen and a better separation with helium. Here's our tick comparing the back end of the hydrogen versus helium. So we see some splitting with p-isopropyl and 1,3-dichlorobenzene when using hydrogen, whereas we notice coelution with helium. So not completely separated, but some coelution, but similar retention time and response and peak shapes. Lastly, here's a quick look at the tick overlaying a 20 ppb water versus a 20 ppb soil via hydrogen and carrier gas. As you can see, we still receive similar responses and retention times. Slightly higher response because of the heating method and parameters used during the soil method, but still similarities. Well, I hope you found this webinar useful. If you have any questions, feel free to list any future topics or email me with any questions at the link email below. Till then, be safe and enjoy the rest of your day.